trusted your word, believed in your quest. Now I see through just like all the rest. Trusted your word, believed your lore. Now I see through, can't trust you no more. Lies and deceit, it's all I see. NASA, you've been lying to me, but deception's a game you played every day. Lies and deceit, it's all I see. You betrayed my trust with your fake streams. I stopped being blind, admit your unjust lie. Remember when the Challenger blew up? We all believed you then, but then we saw those people alive and well. We began to see you.
All right, hello and welcome to Celestial Theodolite update number 11. Tonight, Dr. Mike is going to get into an update presentation to open us up, and then we're going to give a little recap of some of the points made on 11, and then we will get into open Q&A whenever you are ready, Mike. Oh, and as always, if anyone has any questions while we're going through this, feel free to ask. But if it goes on, too long, we'll have to circle back to it because we were trying to keep a schedule. But if you have a question, though, go ahead and ask it while it's fresh. And if it, like I said, if it goes on, we'll just come back to it. But go ahead and feel free to jump in.
And if I need to go back to something, ask me to go back to. So I shared some slides, and this is going to be a back to basics, where we're focusing on some fundamentals that are kind of getting lost. It's one of those basics is it's common for even a simple hypothesis to contain too many assumptions and variables to ever be proven. So instead, it's essential to refute the opposite and mutually exclusive null hypothesis. And then something I've said in the past, not at Earth Awakenings, but elsewhere, is remember to always keep it short and simple. So this is as short and simple as you can make it. Hypothesis is Earth is a globe. We can't prove that, so what we want to do is refute the null hypothesis that Earth is flat or not a globe, if you prefer to say it that way. And Pikes Peak is visible from my house, so that became my personal prime target. From the flat Earth perspective, the flat Earth angle to Pikes Peak should be 2 degrees 31 arc minutes, and the globe Earth angle to Pikes Peak should be about 2 degrees 17 arc minutes, and that's under ideal conditions prior to any correction for refraction. And that number varies from day to day, from hour to hour. The most important thing to understand is that if the Earth is a globe, the angle to Pikes Peak cannot be near the 2 degree 31 arc minute predicted flat Earth angle. It must be closer to the 2 degrees 17 arc minute globe Earth predicted angle. And a modern terrestrial theodolite, the kind you use on the land for surveying, measures the 2 degree 17 arc minute globe Earth angle. But an antique theodolite measures the 2 degree 31 arc minute flat Earth angle. So we have a discrepancy for some reasons. And among other things, it quickly became clear that refraction has been a continuous problem with all terrestrial theodolite measurements of mountain peaks. That's the problem that comes up over and over and over again. So to bypass the problem of refraction, about half a year ago, I proposed using mountain peaks as the horizontal crosshair of a celestial theodolite, and then using the true, which is the uncorrected, elevation of the star at the time of occlusion to compute the altitude of the peak. So we'll assume if it's a straight line of sight and it's a flat Earth, then the angle of the star on the peak should be the same angle that would be predicted for a flat Earth. And that concept consists of just recording what time, what peak occludes what star. And in that way, it doesn't matter where the peak or the star appear to be. It doesn't matter what path the starlight took before it disappeared. The only thing that matters is that it was the peak that occluded the starlight. So it's a simple concept. I just began entering data into a spreadsheet for various mountain peaks, including various stars. And this graph compares raw measurements to flat Earth versus globe Earth predictions for what the elevation of those peaks were. The cyan line on top shows how much globe Earth measurements deviated from the globe Earth predicted altitudes, and that's with atmospheric correction turned on. The green line on the bottom shows how much globe Earth measurements deviated from the globe Earth predicted altitudes with atmospheric correction turned off. And then finally, the red line in the middle shows how little flat Earth measurements deviated from the flat Earth predicted altitudes with atmospheric correction turned off. So from the very beginning, it was clear that the measurements confirmed flat Earth predictions to within a few arc minutes. And that kept going until very strange things happened at North Peak and Blinn Mountain. In the case of North Peak, that was about 80 miles away. So that was the farthest distance any inclusions have ever been observed. And it's still very hotly debated what happened at those last two peaks. But it turned out there was a very simple fix for that. And the simple fix transformed all of the sloppy measurements into clean and accurate measurements. And consequently, the simple fix itself was hotly debated. And that's because our globe Earth friends like to complain that our data is too sloppy until we reach a state of near perfection. And then suddenly they switch to arguing that our data is too precise. And in all cases, our globe Earth friends try to argue that whatever we did was wrong. And for those who are wondering, that big dip in the globe Earth lines at North Peak occurs because the star is allegedly too far below the peak to be measured. And yet, when you look at the red line, there is no deviation flat Earth measurement from the flat Earth predictions. In other words, the red flat Earth deviation line is on top of the zero deviation line. And that was an important revelation because it demonstrated that the flat Earth prediction was correct, while the globe Earth predictions were very, very wrong. So I came up with a J factor which aligns the stars with the globe Earth altitude of the peak. And this was named to acknowledge Jesse's contribution to this, as he suggested we switch to a NOAA site, which is far more precise in measuring the distance. And that gave me the idea, why not make everything much more accurate? And the J factor is a simple fix that cleaned up all the data for both flat Earth and globe Earth measurements. Although some people try to make this much more complex than it is, the J factor simply aligns stars with the globe Earth altitude of the peak. In other words, it makes the uncorrected globe Earth prediction as perfect as our globe Earth friends claim it is. And because of that, it's kind of disingenuous for our globe Earth friends to claim that perfecting their measurement is somehow some kind of a dirty trick. They hate it because that simple fix the measurements and exposed the truth they didn't want anyone else to see. And that truth is that their uncorrected globe Earth angle is half of what creates the illusion that the flat Earth is ellipsoidal. And the other half is G.G. Bennett's celestial refraction correction, which also creates the illusion that the flat Earth is ellipsoidal. And when you take both of those together, it kind of hides the fact that they're taking both of those in opposite directions. So the uncorrected globe Earth angle is a reading that's below what they predict. G.G. Bennett celestial refraction correction gives an elevation that's above what they predict. So it was really ingenious for our globe Earth friends to hide half of their illusion in each place. And on the next few slides, we'll be examining all of these equations more carefully. So this diagram returns to Pikes Peak as an example. As my spreadsheet evolved, of the occluded stars matched the red flat Earth predictions and did not match the cyan or green Glober's predictions. And it was necessary to refute flat Earth predictions to refute the null hypothesis. Thus, the celestial light fails to refute the null hypothesis that the Earth is flat, and instead of falsifying null hypothesis, it actually falsified the hypothesis that the Earth is a globe. And the equations in the upper right corner, Earth angles, derive from the corresponding flat Earth angle. So in other words, all of the globe Earth angles are just offsets from the flat Earth angle. So you can see the theta sub f, the main flat Earth prediction, is just the arctangent of the rise over the run, just what you'd expect. In past presentations, I've given a more complicated version of that for the globe Earth angle, the green theta sub g. There's a simpler, just as accurate way to present that as it's the flat Earth angle minus distance angle. The distance angle is just 360 degrees times the distance divided by 2 pi r. And 2 pi r, most people approximate as 40,000 kilometers, just the alleged circumference of the Earth. And then the theta sub r, that's the refracted angle. That's the one a theodolite, a terrestrial theodolite would measure. That's just the globe Earth angle plus in its refraction. Since the globe Earth angle is the flat Earth angle minus the distance angle, then that refracted angle is the flat Earth angle minus distance angle plus the G.G. Bennett refraction angle. Well, it's because the globe Earth angle is a sham. Our globe Earth friends desperately don't want us to perfect it. That's why they're arguing so hard. You can't make that perfect. That's cheating, or that's a fudge factor. No, we had no way of knowing that when we made that one perfect, it would make everything perfect. So consider what happens to the globe Earth angle as distance approaches 0. You should see that the zero distance, at 0 distance, that globe Earth angle becomes flat Earth angle, because the flat Earth angle minus 0 is the flat Earth angle. And so they become one and the same angle. And that's why our globe Earth friends want to get as close to peaks as possible rather than as far away as possible. They're trying to make the globe Earth angle match the flat Earth angles so you can say, see, they're the same. So in other words, the globe Earth angle is just an illusion. It is entirely produced by pretending that it and the distance angle are real angles. In reality, only the flat Earth angle is real. All of those other angles exist solely as figments of the ellipsoid in the minds of our globe Earth friends. As the distance angle and the celestial refraction angle approach 0, star deviation at each peak could approach any angle. But instead, the star elevation at the peak always approaches the flat Earth angle, because that is the one true angle. So these are the fundamentals of what we've been discussing. And I wanted to make sure to get that out there right at the beginning so that we can all be focusing on the need for a null hypothesis and why all of the angles other than the flat Earth angle are just fake additions and subtractions to or from the flat Earth angle. Are there any questions about that and anything you want to go back to and rediscuss?
Yeah, real quick, can you go back to the slide with the 3 different trig predictions on it?
That one?
Yes, sir.
Is that
Yes,
okay?
yes. So there's been some confusion about what this is supposed to represent. This is consolidating three separate diagrams of elevation predictions into a single diagram using color coding and a tangent. So each one of these represents a tangent to a different elevation. So like one would be the corresponding globe angle because of course the globe makes two separate predictions for elevation to peak slash elevation to observer. But the tangent that you could draw based on the occlusion timing is what is represented here in the diagram. So if that helps to kind of clarify what this is supposed to mean in regards to does alpha equal alpha and things like that. It's like at that exact time, the geometric implication, if you drew a tangent, would be that it is. So that's what that's representing there.
Yeah, in my mind, somehow it made sense to all draw all three of those on the same triangle because they're all derived from the flat Earth angle. So you can see the cyan colored refraction angle, the 2 degrees 17 arc minutes, is really the flat Earth angle minus the distance angle. Oops, sorry, I'm looking at the wrong line. That's actually the globe Earth angle, the theta sub g, the green one, plus the GG Bennett refraction correction. The green angle, the theta sub g, the 2.04 arc minutes, that's what's uh, sometimes called the uncorrected globe Earth angle, but that's really the flat Earth angle minus the distance angle, and the distance angle just being 360 degrees times the distance over the alleged circumference of the Earth.
Awesome. Okay.
Any questions?
So I think there was if there's no questions, we had a big uh, or an important question from last week was about stellarium and what is stellarium. So all stellarium is referencing is the true position of the star plus 15 degrees per hour. And the true position of the star is just a snapshot of where the star was if an observer was taking a zenith measurement on the vernal equinox on the date of whenever they started recording those to make the almanac. So each one of those stars that has a GP to it for cell nav or that's referenced, um, uh, all it is, right, is you just take that position and then you add 50 where it would be 15 degrees per hour from now, and then using Greenwich uh, uh, as your 0 point, you just add 15 degrees per hour from that, and then with your local time added on, that's where you get that's where you get where the quote unquote calculated true position of that star would be. So we're using that as the calculative reference for where the star is going to be. Now, does that make it a globe tool? Well, not yet, because to make it a globe tool, you have to tie all of those single zenith measurements together in time. And they do that by using a fictitious observer at the center, right? So they take the celestial sphere model and the terrestrial sphere model and they merge them using a fictitious observer, setting the altitude of the stars to 3959. So that's the way that they're able to use that from the 0 point from Greenwich and then 15 degrees per hour out. So that's the backbone of the whole system. And what we're doing here is we're testing the basically is the star where it should it, like the globe would predict that it's already been occluded or that the star's already gone, and we're basically testing that. And what we can do is we can backwards derive a distance out of that just using the occlusion timing and the peak that did the occlusion. And we could find our distance. Now, on the globe, you have to tell the globe, for your input, you have to tell the globe where you're at and then reference it so that will tell you where the stars will be based on that, based on your time of where you're at. So the big difference there is that we don't need to tell Stellarium where we're at. We're testing to see if the stars are where Stellarium says they're at. And what we found is that the occlusions intersect with the angles that correspond to the flat Earth predictions. So, what the significance of that is when we're dealing with refraction and this method here, the physical what we've uncovered is that occlusion is a physical intersection. It's not apparent, like an apparent mountain or an apparent object will never occlude a light source. We've got several videos of that demonstrating that there will be a different intersection angle for when the bent light from the medium uh, intersects with the true position of that object in the light source. So there is a physical timing difference that's produced by refraction, but on the end of which we're observing and recording time, all like we don't need to account for it on our end because the timing of which we can't see it corresponds to when it's physically blocked, and that's all that actually matters. Like the moment that we can't see it. So that's the significance of why this method doesn't include refraction on our end, is we're only concerned with what the physical elevations that would actually do the occluding. We're only concerned with where those are at. So where does the globe predict this elevation is versus if there's no drop off geometry, what would a flat earth predict the elevation would be? And if that angle corresponds to where the true position of the star is, and you can no longer see the star at that time from the peak, then the geometric relationship to an observer X amount of distance away would be this diagram that we're looking at here with three separate tangents.
There's also the video of how refraction can't occlude objects in the chat. It's a knife and a laser. It's a very good indication of what you just said.
Nice. Yeah, shout out to Taylor who did that one. That's a quick and easy one to grasp. And then what Goose did, which we'll have to make a little GIF for that one. But what Goose showed last week, if you go to Celtheo update number 10, during the intro, we played a couple of videos, and what Goose was showing was that the angle physically changes. Like it's different when you add refraction. It's not the same as when it's not refracted. So what that shows is that there's going to be two separate timings that would be produced out of this.
Right, and it would also say that any actually attempt to save it via refraction is doomed from these two physical examples.
I am here and do have questions when it's my turn.
Yep. All right, before we get to Jesse, does anyone else have any questions? Flat Earth or globe side, we're here for maximum clarification.
Come on, guys.
Beast, what were some of the questions that were coming up earlier in the week that you heard?
Jeremy's question.
Talking about. Oh, okay.
What
So
if
Jeremy's question regarding the difference in elevation of observer and occluding peak.
Yeah, so if you're on a taller mountain peak and you're observing a different mountain peak that's shorter than yours, right, where it's a different elevation, it's lower, and then you're seeing stars get occluded by that mountain peak, what would that imply? Would that imply that the star, you're higher than the star now, or?
And I have an example of an answer to that very question I can share. And here it is, Cottonwood Pass. I put Cottonwood Pass in the sheet as viewed from Pikes Peak, which is Pikes Peak is about 4,300 feet. Cottonwood Pass is about 3,700 square feet. So when
Meters, right?
yeah, sorry, I meant meters. Thank you for correcting me on that. So it's looking down 609 meters to Cottonwood Pass, and it measures that angle correctly. It ends up being about 5 meters low, and then on the graph, you can see it right here. The cyan line, globe Earth prediction is way off. At the red line, you can see it's hard to see on this scale, but it's a measly little 5 meter dip below what it should be. And this particular spreadsheet has a few little humps and minor dips because of some playing around I was doing. But I set out accidentally tested that because I didn't realize Cottonwood Pass was lower than Pikes Peak. For some reason, I didn't realize that, and so it ended up looking down, and the celestial theodolite handles that with no problem at all.
I think Andrew's hot miking.
I didn't even know you. I was throwing that around as a hypothetical. I didn't even know you could get a star below your horizontal. But if you're saying that star is in its actual position and it's being occluded by a mountain that's beneath you, you're above the star.
Well, the angle has no indication of its elevation, like if it's above you or not. That's just the way that it calculates out based off of the occlusion difference.
Yeah,
Like
but you're above the
it's not physically at that level, right? It's still above, right? It's just how you see it. So the calculation comes out that way.
you're above the mountain that occluded it, though.
That's why it comes out negative.
Yeah, that would mean you're above higher than the star.
But in reality, you know that you're not.
I know, but if this thing is giving us actual positions of stars and mountains,
Well, this is essentially
So
what this is what a dip angle is in celestial navigation. Essentially, it's a similar thing. Doesn't mean you're above it. It's just the angle from your viewpoint.
right, it's just an angle from your viewpoint, and if you think about it, these mountains are both several miles high, and you're only looking down 600 meters. But it does demonstrate that you can successfully look down on another mountain and see that other mountain, including a star, it's at a lower angle. So you're having to look down. Let me see what that angle was. I didn't pay any attention to the angle. So it says that's negative. It's only negative 17 arc minutes. So we're only talking about a sixth of a degree downward. It's hardly noticeable. Because both of these mountains are about almost 3 miles tall, you can pull that off with these particular mountains.
so the mountain and the star would be below your, since you got a negative, that means that if you made a horizontal there, it would be below your horizontal, right?
Correct.
Correct. So that means if everything's geometric in its actual position, that means that you are above the star.
So above the stars is probably a wrong way to look at it. What this is saying is the true location of the star is a negative angle with respect to the observer.
Beneath you, yeah, I know. Yeah, you're saying you're at a
So
higher
so
elevation than the star.
right, you are definitely at a higher elevation of the star. It's and if you're talking about a horizontal tangent drawn through the observer, yes, it's below that horizontal tangent drawn through the observer. And
That's only a problem for me, no one else.
why would that be a
I
problem?
agree with it.
Explain it.
Because I don't think we can get higher than I don't think we can get a star below us. Like I don't think we can be above a star.
It's physically not.
Propagate the light ray back from your
It's
position.
not. It's your perceived angle at that elevation with respect to the other thing. Like it only works in that specific instance.
Well, propagate the light ray from your position at a higher altitude to the other star, the other mountain at a lower position, and follow it through. Where did it stop? Where did from your mountain to the other mountain? It's losing altitude at constant rate all the way along there. It's to that other mountain. When did it start increasing in altitude? How far beyond that? Because obviously you're saying the star is in higher altitude than both mountains. So isn't that a concession that the line is radically curvy?
What?
That was
That's
a globe
retarded.
Earth perspective on all of
That's
this, but
retarded.
um, uh, the whole reason that the celestial theodolite does it this way is to eliminate refraction. So any other time a globe Earth advocate would be arguing, oh, refraction lifts it. that 17 arc minutes, but now you want to claim that doesn't happen. So I'm a little confused about your position. Could you explain it better?
Yeah,
You talking to me or the other guy? Oh, that guy.
in the one?
Pause up.
Yeah, there's
In the
probably
one you
two things. Pazza might be jumping on this as some kind of globe Earth thing. I don't think that's Jeremy's
No, I'm not.
approach on it. So these are two
No, I'm not.
separate things.
I'm jumping on
think-
I'm not
Jeremy's
with that.
position.
I'm not with that dude at all.
No, no, but you're at one. You're on one mountain. You're looking at occlusion of the star occurring on a lower mountain. So, as a thinking exercise, propagate that light ray back from your eye to the other mountain. It's losing altitude, that light ray, all the time to get to the lower mountain. What happens at the other side of the lower mountain? Indulge me. What altitude does the light ray stop decreasing and start radically increasing? And if that's what's going on, isn't that a concession that the light is curving?
Well, every time I hear curve, that makes me think this is from a globe Earth perspective.
Well,
When
no,
I've been on
listen.
top, well, listen to me. I've been on top of Pikes Peak many times. You can look all around in every direction from Pikes Peak, and you see sky right up until you hit the horizon. What this is saying, although Cottonwood Pass is lower than Pikes Peak, it's still higher than the horizon. That's
Okay.
that concept.
Okay. So that's the answer that Vectory means that Jeremy's assertion that because the star's lower than you, it must be this. You see the star lower than you, he's definitely lower than you.
Well,
That's the answer to that question, isn't it?
out of curiosity, how much closer was the flat Earth to be negative than the globe Earth prediction to be negative on that ridiculous example that you pulled up? Because they're both negative predictions, right? How much more negative was the globe prediction?
The
Yeah,
globe Earth does.
the globe Earth says it's negative by 2,800 meters with refraction off. It says it's lower. Let me see if it even says it's lower with refraction on. No, with with refraction on, it says that it's 1,700 meters lower.
Right. So the observation itself doesn't really have to do with the celestial theodolite method. It's a differentiation between each model, right? We're looking for a mutually exclusive. So if we're going to entertain negative values in this one-off example, we should note that again, the globe Earth is far more negative and thus wrong. The method works either way.
But being higher than a star though is an issue for me.
Well, like if you're looking at
Well, the horizon's apparent though. So
right. So if you're
you
looking
know
at
that
a
the mountain
commercial,
peak isn't like it's just a character. All right.
right?
But the
It's
mountain peak
perspective.
is like what could be called like an artificial horizon, perhaps, because it's not like the horizon. It's a mountain that's higher. Sort of like if you see the sunset, where it gets occluded by a mountain just when you're on the ground. That's not where it would occlude if it was out over the ocean. That's obviously it's like an artificial sort of horizon. It could be called because it's much higher than the ground.
Hey, can someone point me to like a simple like a video explaining the celestial theodolite with the occultation of the star? Because it's hard to understand. I'm trying to find like a simple explanation of it.
Okay, so if we're not above the star, then that one with the negative angle, that's not all geometric then.
No, it is. It's just below your horizontal from your perspective. That doesn't mean it's altitudinally below you.
There you go. That's a good way to put it.
It would have to be though. If you make a horizontal and everything's all geometric, everything below it is below that horizontal.
But these are
Geometric.
observations independent of the method, right? Like this is an observation that he made, whether the Earth is flat or a globe. This is what it looks like in reality. So we can speculate on like what that means theoretically, but the observation, of course, for this meeting, mutually exclusive globe still fails, applying the elevation prediction for that apparent angle, right?
Apparent being the key word. So you're looking at a jet plane that's above you at 30,000 feet, looking straight up. Now, an hour goes by, you look at the horizon and it's an inch off the ground. Does that mean that you are higher than that jet plane because it's an inch off the ground? No, it's apparent.
Yeah, but if this celestial theodolite gives all actual geometric positions, and you make a horizontal and something's beneath that, and you're saying this is all geometric, then that is beneath you.
It's geometric to an apparent position because obviously it's compressing to the horizon due to optics, and that's what's being measured.
So then it's not geometric. It's an apparent position, not actual position.
Geometric, just like the stars look like a dome over your head. It's not literally a dome. It's due to your perspective that you have these angular differences. It's not giving you a true it's giving you not giving you a true elevation, because obviously we don't know what their true elevation is, but due to your perspective, we're measuring the angular elevations. You're not higher than a mountain just because you
then the elevation would be your angular perspective. But
right.
All right, let's see here. There was Shane, if you could pull up the link that I showed real quick.
Yeah.
We'll cover the quick explanation of the celestial theodolite.
Are you happy, Jeremy? I got you.
No, I'm not. You didn't get me. I'm not happy. I disagree with everything everyone's
No, I'm
saying right
saying
now. If you're,
are you happy that I asked your question? I got your question up.
yeah, I'm happy. I'm happy, Beast. Thank you.
Jesus, Jeremy. No, I'm not happy.
Overall, though, I'm not happy.
Alan, are you about to do a quick rundown of celestial
Yeah.
theodolite just for like a?
Yep.
Yep.
Well, just to finalize that, I mean, Jeremy, we could talk more about that on other times, unless you feel like there's more to discuss on that now.
That's fine.
It does get into
No.
other, in terms of perspective and optics and over distance and altitude. There's a lot more factors to discuss. But it is cool that he had one that actually is a negative, and compared that to what the globe versus planar would show. So that is.
I couldn't believe it. I've actually been tossing that around as like a hypothetical, theoretical thing that maybe if you did see it, I didn't know it was actually done.
Nice. Here we go. Shane's got the little video up.
Thank you,
Word
Shane.
salad.
What we're looking at here is the celestial theodolite method. What you can do to participate, how to do this, is you just record your observer location coordinates, and you set up your recording device, and you record a peak, and then you look up the coordinates of that peak later on. And if you can get it centered on the peak, that's great. But if you're off a little bit, you can play around in Stellarium to figure out where you actually got the occlusion at or whatever. And then you could calculate your elevations and stuff based off of that. But the basic premise here is what we're looking at. If you could replay that, Shane, just over and over again while I talk, is this star occluding. We're looking at the apparent position of that star, and then when it crosses that mountain peak, it's no longer visible. So what we're doing is we're referencing in Stellarium where the true position of the star is, which is the calculated position with respect to 15 degrees per hour, and using the vernal equinox as the snapshot for where, like, the starting point for where the star would be at the 0 point, and then with 15 degrees per hour where it would be. So using that unrefracted true position, we're looking for a geometric relationship between that and the time in which it gets occluded, because the globe would predict, if you gave it this location, that the star would be celestial refracted and it should still be visible. So that's the basic rundown and premise, is we're testing the angles to the stars and based off of occlusion timings, because refraction, right? If there's refraction on one side of the lights on the other side of the mountain, then that timing is still going to produce a physically different time, because this cross section of this video that we're looking at here is 44 arc minutes. So to half of the screen is 22 arc minutes. This little dot is like what? Like 1 arc minute. So when we have a physical occlusion, like I said, the angle is going to change based on refraction on one end, but it's still going to result in a different timing. When we're dealing with this little point source of light, that physical occlusion, celestial refraction, basically can't always make up the entire difference for what it would be if the Earth was flat, as otherwise the globe is just pretending to not be a flat Earth using celestial refraction coefficients to adjust the timing to explain why the star is still visible, because there should be no geometric relationship to an observer X amount of distance away and this mountain peak, because we've never told Stellarium where we were observing this from. So what we do here when we do our referencing and calculations, we calculate what the relative angle to the peak would be, and then we go to the peak in stellarium and we wait for the stars to line up with that geometric angle. So we so then when they're lined up in with the peak at the peak, there should be no relationship to them being aligned to an observer, X amount of distance away. It should be below it, because if the globe is real, then the angle would be lower, and the stars should still be visible. They shouldn't be occluded at that same time. So hopefully that makes sense and adds some clarification. If you need some more, if you have some additional questions or whatever, feel free.
Yeah,
That star.
I'll have to listen to that over and over again, but I'll get it. That's the way I work. I just listen to things over and over until I understand it.
Awesome, no worries. I'm the same way, so don't worry about it.
Okay, thanks a lot.
I take it you created a custom landscape to put into Stellarium.
Yeah, so Jesse found some tools where you can take mountain peak silhouettes from peakfinder.com or .org, peakfinder.net, something like that. You can export the silhouettes into Stellarium, and then you could go to observer location, look at what the peak would be, and then there's actually a little custom reticle in Stellarium that you could add for the type of camera that we have. So Shane, if you go to slide 6 on there real quick, you can see the mountain silhouette and the Stellarium reticle on there.
I had that up. Hold on.
Oops. 1 second. We'll show you the comparison there. And then if nobody has any questions, we'll
I just had one more question.
Okay.
Do you know what star catalog you're using in Stellarium?
I think it's one of the Gaia's 2 set or whatever.
Okay.
What I like about these things, sorry.
Yeah. Oh, you're
Yeah,
good.
what I like about these things,
This is the Stellarium thing that Jesse found, where you can import the silhouette, and then you can line it up to your frame. Very cool.
Yeah, that frame is specific to the type of C star frame, right?
Yeah,
I like these too.
Theoretically, you could use ChatGPT to make your own for your camera, theoretically, I suppose, and then have your own right there, which would do the same thing, but it would be relative to your camera.
If I may, you can also just.
Oh, sorry. Yeah, go ahead.
I was just gonna say, you can also just look up the sensor size and the focal length and the pixels count of your camera or whatever, and just put that all into Stellarium, and it figures it all out.
Oh, nice.
So I've got a question.
Yes.
So doing all this analysis to verify that from this given location, I guess it's Pikes Peak, what stars are up in the sky at what angle at precisely a given time, right? We have this nice table now, the location and the time. Could now they go to a different peak, maybe, within the Colorado, within the Rockies or whatever, and then be able to use flat Earth calculations on a flat Earth to show the geometric relationships to predict the angle of that exact celestial body at the exact moment in time from the other location?
That's a fantastic question, from the other location. So, yes. And he's used different mountain peaks too, so at different distances. And I think Jesse even made a simulator where you could simulate out what the different possible angles and elevations would be. So it definitely, the answer is yes.
Right. So I guess where I'm going with that is, so then ideally then you'd be able to say, okay, this star is at this angle in Pikes Peak, Colorado. But if you were observing this star, let's say in Miami, Florida, this is the angle this is the angle that the star would be at, and here's the flat Earth math that shows why the star is now visible at this angle from this location on the flat Earth and at this angle at Pikes Peak on the flat Earth.
Yeah, I misunderstood your question. So that wouldn't be related to celestial theodoliting. That would just be adding 15 degrees per hour to the position, to the true position of the star from which it was occluded. We could do something like that, but that hasn't been.
No, not 15 degrees. I mean, at the same exact moment, like at the same like UTC, like at the same moment in time, at the angle and position of the star, like the angle of elevation and the azimuth of the star in the sky from Miami, Florida, and Pikes Peak, Colorado, over a flat Earth. Where is the mathematics to show the prediction of where those objects are? And then, therefore, once you have that flat Earth map, you can demonstrate we live on a flat Earth because we can now mathematically predict all the geometric objects in the sky, or all the celestial objects in the sky using flat Earth geometry.
See what you're doing. So they already did that though. And then to tie it all together, like you're saying, so that we could tell where it would be for an observer in Florida and stuff, you have to put an observer in the center of a fictitious coordinate system and make it all relative to that.
Do you?
Yeah. That's how the quote unquote globe works.
Well, is it?
It's exactly how it works, yeah.
No, I don't think it does. All right, you don't have to imagine you're in the middle of it.
No, you absolutely do. It's the reference point for setting celestial objects so you can do celestial navigation and use stellarium, quote unquote, use the globe, etc. It's exactly what you have to do.
Yeah, how else would you take an angle, Pazza, if
Without
you didn't
geocentric
do that?
coordinates, you have to
Well,
use
Well, you can
comparative.
take angles from the surface, can't you?
Yeah, but all those
Or it's
angles,
What-
according to you, are pointing to a specific place.
so you agree that
Yeah,
this
but
is flat Earth
when
evidence, and you want to talk about something else? Is that what you said?
when a sailor uses this theodolite, he's not propagating an angle back to the center, is he?
How did he set up his horizontal plane of reference?
Okay, that's a different question to the one I asked.
So just take
Yeah,
a theodolite out, don't set it to a horizontal plane of
So-
reference, and take
No, I
a
didn't say
measure.
I didn't say he didn't do that. But when
Yo,
he measures an angle
real
to a
quick
star,
here,
isn't that?
we're going to go over the Shane, can you screen share real quick so we can go over the J value and the spreadsheet situation?
Oh,
And then we'll
Mike's screen sharing. Oh, never mind. Okay, all right, I got it.
Yep. And then we'll have Jesse ask a couple of questions, retouch on the stuff from last week, and then we should be able to wrap up here within the next 30 minutes or so.
Hey, it's the KF. Thing.
Did someone
All
say
right,
something? Oh, sorry.
So we got the new calibration method, right? By aligning the azimuth timings or whatever, which made everything perfect. But even not using that, right? Like, let's say we don't want to use that. Look at the before and after for where we were at in the analysis without the corrections.
So this is with the corrections, right? The blue line meaning our prediction, whatever. All right,
No,
this
this
is
is without.
yeah, sorry, this is without the corrections, right? So this is what it would be.
No, this one's with now.
Dude,
Now you
no
said it
J
backwards.
value. No J.
This one has the J value, bro. This is no J value. J value. No J value. So the zero is like, the prediction, and then deviations from that are being plotted out. So if anyone would like to participate in this, all you have to do is have a device that's capable of recording and a star at night and defining a silhouette of a mountain peak. So if you have equipment good enough for that, and it's able to sync to GPS time, that'll make your job a lot easier. So do your recording and then record your latitude, longitude coordinates, and then look up whatever peak you're looking at. And like I said, if you can get the peak centered, that's obviously ideal. But if it doesn't turn out that way, you can always look it up later on the back end. But you need that reference for where the peak would actually be, so you can calculate everything after. But that's all you need to participate. So anyway, if there are any questions, if not, we will move on to some of the contentions that Jesse had from last week, and or new contentions for this week.
Yeah, I was gonna ask, but yeah, go ahead, Jesse. If it's about your quote unquote fudge factor, then I'm all ears.
Okay, that is one of the things. But I do want to make sure that I have the foundation of this right. So I really wanted to ask Dr. Mike, at the time of occlusion, sir, is it your claim that the geometric elevation angle to the mountain is equal to the geometric altitude angle of the star?
Could you repeat that question, please?
Yes, sir. At the time when the occlusion is observed, is it your claim that the geometric elevation angle to the mountain is equal to the geometric altitude angle of the star? In other words, non-refracted angles, just the geometric angles of those two.
I'm going to have to ask you to repeat that question one more time. Sorry about that, Jesse.
That's okay. So, at the time when the occlusion is observed, is it your claim that the geometric elevation angle to the mountain is equal to the geometric altitude angle of the star? And this is I emailed you this question last night.
Yeah, it's the phrasing of the question that's throwing me off. So I did a screen share that shows what I'm saying, and what I'm saying is theta sub f, which is the flat Earth angle, relative to a um, flat topographical plane that goes through the observer. Relative to that plane, the angle from the observer to the mountain is this same angle at the true elevation of the star has relative to the mountain peak that's occluding it. So in other words, theta sub f is the angle from the mountaintop to the star, and it's the angle from the observer to the mountain peak if this were a flat Earth. So they're one and the same angle, and that's what needed to be refuted to refute the null hypothesis. So because they are the same angle, that is not refuting the null hypothesis. In other words, it's behaving exactly like a flat Earth would behave.
So I think you're saying that you are claiming that at the moment of occlusion, the mountain peak and the star are in a physically straight line, right? With the observer.
The from the observer to the mountain peak onto the star, that's a straight line according to the nautical almanac. So that's the contention. That's why the final bearing is so pivotally important, because when you look at bearings on the map, you see that bearings are curving constantly on the map, and that doesn't matter whether you're looking at a globe Earth map or a flat Earth map, or they're basically all curving all the time. And so it's important to know that the initial bearing, which is the direction the observer is looking toward the peak, is not the same bearing that the peak is looking to see the star. And yet, despite the fact the bearings are different, it is a physical straight line. If only you could see that star where it really is. And of course, it's a well-known fact that actual refraction prevents people from seeing where the star actually is, which is why the theodolite uses where the star is known to really be rather than where it appears to be.
So I see you have is that theta f equals 231, and then again you have theta f equals 231, right?
Right, and what that's indicating is it's the same angle from the mountaintop or from the observer on the Earth. They're both experiencing the same angle.
So at the time that the occlusion is observed, then the non-refracted, the geometric straight line angle to the star and the mountain would both be 231 then. That's what you're saying?
They would both be 231. That's correct.
Okay, good. So it sounds like the answer to my question was yes. At the moment of occlusion, the geometric angle to both the mountain and the star are the equal elevation angle.
I had, for some reason, I had trouble following the question the way you phrased it, and I'm sorry about that. But
it's not
this
you.
diagram basically says it all. It's the same angle.
All right. Now that you have that clarified, Jesse, are you going somewhere with this?
Well,
Certainly. If I may.
Okay.
So, Dr. Mike, did you see Goose's demonstration where he showed that the elevation angle to the star would be unequal to the elevation angle to the mountain at the time of occlusion if there was refraction at play?
That is not what his demonstration showed. He showed his demonstration very elegantly shows that refraction changes the apparent position, but we're talking about the true position here. That's why we go to the uh, basically the nautical almanac, see where is that star really, not where it appears to be due to refraction, but where is it really? And then the other equations on this slide, um, they show you the where it appears to be refracted, where it appears to be on a uncorrected from a globe Earth standpoint, and we're talking about at least three different angles depending on which correction you're applying, because the globe Earth angles are all corrected angles. The flat Earth is the only angle that's calculated based on plane trigonometry, and it's the angle that's actually measured.
So is it your claim then that even if the light was curving due to atmospheric refraction, that would not change the time of occlusion?
Can you repeat that real quick? What did you say?
Yes. So
I misheard.
yeah, is it your claim then that even if the path of the light was curving due to atmospheric refraction, that would not change the time of the
Would not.
occlusion?
No. Let me try and answer what I think you're trying to ask. The answer to your question is even with refraction, there's going to be a physical timing difference. It's not going to make it up 1 to 1. So the globe still has to have a different timing.
Someone's misunderstanding the video demonstration in chat with the laser and the knife as well. Like once it's like you can't be like just because it's refracted doesn't change the time, right? So
No, it does. If it's refracted, then on the
no way.
so like see, I think about it like this. So if the knife, if it's just a knife in a cup, right? And like let's just say that the cup isn't refracting, right? There has to be a medium in the cup. So like the cup is just pretendsies right now. So the laser and the knife intersect at like the exact physical point where it's like you could take a stick and line it up and they would, be touching the stick, right? Now if you add water to the cup, you have to move the light in a little more for it to physically be occluded by the thing. But after that point is met, like that physical intersection condition is met, the observer on the other side that's seeing the refracted light and object no longer see it. So it produces a different time, even with refraction. That's why like when we say we don't care about refraction, like we're not saying it doesn't exist or won't impact it. We're saying it still results in a different tangent. Which is what Mike is showing now with that diagram there.
So refraction could delay the the occlusion, right?
For a little bit, yeah. And it, yeah,
So
it won't. But you understand that it can't make up the entire difference, like where it's like 21 arc seconds below a physical object. That's like it's been below an object for, you know, like 40 seconds, right? And then it gets occluded. Like that's not what's happening.
well, so now I'm getting a mixed message here, because if refraction can delay the occlusion, then the angle that the geometric angle to the star when it occludes later due to that delay will no longer be straight line to the mountain anymore. It will be below that straight line to the mountain, right? If the timing of the occlusion is delayed.
Jesse, the timings in which they're occluded are like, 5, 10, 15 seconds apart. There's still a physical occlusion difference that has to be. This has been the entire premise the entire time.
Can I ask a question after this?
Well, Bacon. I thought Bacon
Go
had a
ahead.
question. Oh, okay.
Go ahead. What's your question?
Bacon will come back in a minute. He'll have a couple questions, but yeah, Pazza, did you have a question?
Yeah, go back to that diagram a second, if you would, please. Or the one
The
with
3 formula.
yeah,
formulae.
yeah, the angle, the triangle, the angle, 2 degrees, and the okay.
That one.
So yeah, so I take it that the theorized arctan rise of a run, that's just based upon trig, based upon the flat surface, 50 kilometers, and the altitude as recorded.
Hey,
Yeah.
Pazza, your mic, are you
Yeah,
far
it's
away
kind of
from it?
cutting
It's
out.
Is that
super
sorry? Is
low.
that better?
Oh, there
Sorry,
you go. Much better.
sorry, my apologies. So
Start over because I
has
didn't hear any of that.
does this
If you can.
does this take into account the fact that if you were on the mountain is 50.7 kilometers, that's 31 and a half statute miles away. If you were on top of that mountain, or at the base of that mountain, in fact, and you observe the same star, the elevation angle of the star, it would be 27 minutes higher than it would be for the guy 50 kilometers away. Is that taken into account anywhere here at all? That would be the reality of observing the star. Because if you're looking at a star, at that instance, anybody 69 nautical miles nearer is going to see it 1 degree higher, and anybody 69 nautical miles further on in that direction is going to see it 1 degree higher. Is that factored in here at all? Because that's part of that's not just a postulation, that's reality. That's how celestial navigation works.
If you look at the two angles, theta sub f and theta sub g, that's where it accounts for that 27 arc minutes of difference. So theta sub g, the globe Earth angle, says that star should be 27 arc minutes lower than what it actually is. So the flat earther says, oh, well, the mountain peak is it's 2,200, 26 meters above me. Therefore, I should see an angle of 2 degrees, 31 arc minutes. The globe earther says, well, that's 1 degree, or in this case, 27 arc minutes across the curvature. So it should only be 2 degrees, 4 arc minutes. And when we go to the mountain peak, unfortunately for globe earthers, it says that star is at 2 degrees, 31 arc minutes, not at 2 degrees, 4 arc minutes. So there's a discrepancy. Discrepancy because it's the very angle predicted by a flat Earth. It can't refute the hypothesis that the Earth is flat, and so we come to the conclusion that the hypothesis is wrong. The Earth is not a globe because if it were a globe, we should be seeing 2 degrees, 4 arc minutes. Or in any case, what we can say with certainty is we should not see 2 degrees, 31 arc minutes. So 2 degrees, 31 arc minutes is what it cannot be if the Earth is a globe.
Whereabouts? From the mountain or from the guy on the ground?
Well, in this case, it's both.
Well, it
Yeah.
can't be both, because if you're stood where the man stood and you observe the star, and simultaneously someone on the
What
mountain
you're
observes a star.
you have to understand what this diagram is showing. This is showing here's what a flat Earth predicts is saying the rise of the mountain is 2,226 meters. The distance away is 50.7 kilometers. The arctangent of rise over run is 2 degrees 31 arc minutes. Therefore, the flat Earth advocate predicts that angle is going to be 2 degrees 31 arc minutes. So at the mountain peak, we look to see where does the nautical almanac say that star actually is, not where it appears to be, but where is it actually, because only where it actually is can block the light, and we don't care what refraction path it's taking. And on the mountain peak, it says it's 2 degrees 31 arc minutes, the exact angle predicted for a flat Earth, which is the one thing it cannot be if that's a false premise.
Right, but
Yeah,
the
can I comment?
the observation of the guy is never going to be 2 degrees 31, is it?
Can I comment something?
You're missing the point.
I think the misunderstanding is that what Pazza is saying is that if you were to go to that other mountain peak where we don't have an observer that you're using to look at that transit, if you were to put an observer on that mountain peak, the angle that's 50 kilometers away, 50.7 kilometers away, that star would not have the same angle of elevation as it at any given precise moment in time. That's identical. When observers making the observation at the same exact moment in time, that star will have a different angle of elevation for the observer on that mountain that's 50.7 kilometers away than from those two locations that are 50.7 kilometers
It'll be
apart. That's
optically
what
different.
Pazza is
Yeah.
saying. That's what
Yeah,
Pazza
right.
is saying, because that's how celestial navigation is done. We know that there is a 1 degree change for every 69 miles or 60 nautical miles, right?
Is there a
Right.
question
So,
in here
Well,
somewhere?
so understand. Well,
I
so
feel like there's
understand
a conflation here. I feel
what's
like
being
there's a
put forward here. So what they're showing, right? If we don't tell Stellarium where we're at, right? If we're being real sneaky, right, and we're going to test Stellarium to see if this model is geometrically true, right? We're looking at the true position of the star, right? So not the apparent position which celestial navigation is based off of. We're looking at the true position, right, which is the calculated value based off of the snapshot at zenith point for the first point of Aries, and then using 15 degrees per hour, right? So there should be no geometric relationship to the relative angle to a mountain peak at whatever distance the observer is away. And when that star gets occluded by that peak, if we're using that peak as the crosshair, right? So that's what's being distinguished here is we never told Stellarium where we were at because the globe, like as you pointed out, makes two separate predictions here. So for the true geometric position of the star at the observer location, it's way lower than the peak, but yet it doesn't get occluded until the time at which its angle corresponds to the peak from the peak. So when we draw that tangent here, we're looking at this triangle, like from the observer to the peak and then to the peak to the star. That's the implication at that time.
correct me if I'm looking at the diagram here, and correct me. The one in the light in the cyan color and the 2 degree or the 2 minute 17 second. That's what the angle of elevation would be on a globe if there was an observer standing at that line at the highest point of the black triangle. Is that what that is saying? And then you guys are saying it's 2 minutes 31 seconds in the red because that's what the flat Earth predict. Is that essentially what you guys are trying to say in that?
Yeah, so we're consolidating three separate predictions into one diagram. So if you look at it from the far right, the observer's looking at this elevation, this peak, and there's three separate predictions here for what that peak would physically be at if there's globe drop, and then if there's globe drop accounting for refraction, and then if there's just a raw flat Earth where there's not going to be any drop from that mountain based off of any distance.
When you said didn't tell Stellarium where you were at, I mean you put the observer's position into Stellarium, obviously, didn't you?
No.
Only at the mountain peak, just to look for. So what we did, right, is you enter the coordinates of the peak and you set it to whatever angle would be the calculated angle that you're going to be based off of your distance to the peak, and then you look in that direction, and then when stars intersect with that angle, you go out and see if you can, like, when you record it, does the star become, like, is it not visible anymore for you at that time? And if it is, then the geometric implication there that we're drawing based off of the true positions of the stars is what you would see this tangent here. So any one of these values that this tangent connects to after it crosses that peak threshold, that could be any one of the timings that correspond to an angle that would be mutually exclusive to either a globe or a flat Earth, just based off of the true positions.
Hold on. Just to be clear here, you guys are putting in the coordinates for what would be at the location of not where the observer is, where you're making this, but at where the peak is, which is represented here at the highest point of the black triangle, right?
Correct. We are entering the coordinates of the crosshair of our conceptual celestial theodolite. So if you could, instead imagine, instead of this being like empty space between us and the mountain, just think of like a giant telescope that extends from my eye to the.
I understand,
Okay.
but my question is, when you're looking for the angle in stellarium, are you putting in the coordinates that's at the top of the black triangle, all the way to the very left of the triangle?
Yes. Yes.
But your observer is on the far right of the triangle, right? Where that's where the actual observer is, correct?
Yes.
Okay. And then, so what did stellarium predict the angle would be for the observer on the top of that, the top of the triangle? Was it the 2 minute 17 or the 2 minute 31?
2 degrees, 31 arc minutes, bro.
Yeah. So the time that it was occluded, if you go into stellarium would say that star is at like 231 or 232, something like that.
Okay. And then, but at your observer location on the far right, you guys measured 2 minute 31 and verified it. Is that what you guys are saying?
So we measured it via the time. So the time that we no longer saw the star is when we're using to make the measurement.
Because that corresponds to an elevation difference. So I think on the left, the colors are like the 3 different elevation predictions for globe Earth in green, globe Earth with refraction in blue, and then flat Earth in red, right? Because the geometric prediction we're using responds to 3 distinct elevations, and those elevations determine the occlusion. So there you go.
So if you were to,
of course, are based on time.
So if you were to send an observer to the mountain that you're using for occlusion, that's at the very height of the black triangle, what would they measure that star at that given moment?
246 is what stellarium says it would be with celestial refraction, and without celestial refraction, it says 231. But that would be the apparent, or that would be the position that you don't actually see. That's the calculated true position. So, but the apparent position it says would be 246 or something like that.
Yep.
So does the globe viewer to mountaintop angle match what stellarium would show, or you guys didn't do that one?
What was your question?
The green angle, right? That's the globe predicted angle to the mountaintop.
Correct. That's the time that would correspond to a globe. So like this,
Okay.
so when you see these angles, they all correspond to different times.
Right. So what does stellarium match that green angle?
No.
It matches the red.
I see. So actually, those observations are not all at the same moment in time.
Predictions.
They are.
Right?
No, they are.
These are predictions.
Yeah.
It's all, guys,
one
it's
snapshot.
It's always the red angle is the thing. This is one example. There's 46 examples of this being the case every time. So
okay, so this was kind of where I was confused earlier in the week. If a glober went out and measured these angles, I would assume they would get what you guys are getting.
Well, when you're talking about measuring, it makes us think you're doing optic angles again, which is not the point. You have to make a prediction using trig and your chosen refraction correction, and then compare that with an observation to get the correct time. Did it occlude at that time that you predicted, or did it not? Mutually exclusive. When you're trying to like talk about measuring angles, that's refraction, disqualified, doesn't matter.
Yeah, to be clear here, like if you were to whip out a theodolite or whatever, the best way to measure stuff is now, like whatever the standard is, if you had the best equipment at observer location and looked at that mountain peak, it would come out to be about 217, 219, or whatever the quote unquote globe predicts. But our contention is that the curvature, that the drop, that is all optical compression, that these are all optical mechanisms, and that it's not due to physical elevation
Right.
loss. So that's why that's how this method differs from like an optical measurement, because using the timing in which a star is at corresponds to an angle and vice versa. So using when the star isn't visible in the relationship of its true geometric position and in alignment with the peak on a flat Earth versus a globe, there should be no geometric relationship to the true position and the occlusion timing. Yet it seems that like every time, like Shane was saying, it works out where the geometric implication is what we're looking at right here, where this 231 predicted angle to the peak is matching the occlusion timing for the true position of the star going from peak to star.
It never matters where the observer on the right is, because the GPS location we put into Stellarium is the mountain peak in the middle, right? That's why all the lines are there.
Well, my point was, if a glober went out and did the same measurement as you guys, I would assume they would get the same thing as you.
Oh yeah, they
And
would get the same time. Yeah.
right, so if they took that angle, which is what you basically, if they did the same test you guys are doing, and they went back to Stellarium, how would they reconcile that Stellarium is inaccurate? Right, because I find it hard to believe that out of all the astronomers we have, no one's noticed that Stellarium is off.
That's not the
I
claim
can
at all.
address that.
Go ahead, Jesse.
Right. I have not found a single case where Stellarium was off. The rest of the story is that when we simply do the time the occlusion, put Stellarium on the peak, and read the unrefracted elevation angle, that only matched flat Earth prediction a few times within a reasonable margin of uncertainty. Most of the time it was outside of the margin of uncertainty. Sometimes, in some cases, for example, I went and timed some star occlusions myself, and also another flat earther did, and we got angles that matched the globe prediction. And there's also angles that match a concave Earth and a tiny globe. So using the method without applying some correction, which is still in dispute, does not specifically match flat Earth. Some of the data points do, but some also match globe Earth. Some match nothing, like concave or in between or whatever. So, but the results are exactly what you would expect on a globe because of the 1 degree per 60 nautical miles.
That's ridiculous, Jesse. All the data is refuting you right in the face.
Hold on. Don't interrupt them. Let them finish before we. Just hold on. Let them
thanks.
go.
So, when they move Stellarium forward to the mountain peak, that adds 1 degree per 60 nautical miles of astronomic or of angle to the star, which is exactly what you would get on a globe. And by moving it forward the right distance, then that compensates for the fact that they turned off astronomic refraction and compensates for globe drop. So if the mountain is the right relationship of distance and height, then their method just happens to match flat Earth. But if it's different relationship of distance and height, then it matches globe or somewhere between or whatever. So, but when I do the math and say what would happen on a globe if you timed an occlusion, put Stellarium on the peak, turned off atmosphere, then I get exactly what these angles are. In fact, I was able to predict what angles this method would give even before locations and stars were measured and occluding. So, yeah, there's more to it than what you heard so far.
Yeah, so my point being that like if I was to go out there and take these angles,
Sorry, my mic was muted.
Oh,
Shane, if you, sorry, Anchovy, I'm gonna reply to this real quick because this is an extremely important point of contention. Mike, if you could stop screen sharing real quick, and then Shane, if you could screen share the graph again.
Mm.
All right. So here we have the corrections applied, right? So this is J value on. Now, Shane, turn off J value.
Hold on 1 second, actually. I had it set to unzig and I did a bunch of other stuff, so hold on.
Unlucky. One second, lads. I'm gonna delete the J value from it. Because the way that it was just framed, it was that it made it seem like there was like the flat, like it only matches flat earth in specific instances. That's the exact opposite. And that's what the simulator shows, and that's what Jesse measured with his measurement, which we'll go over here in a second. As soon as
I got it. It's the exact opposite of what Jesse just said. Yeah, and like I don't know where he's even getting it. He just says stuff. It's ridiculous. Anyway, every single measurement is comporting with what we're saying, and he's like, "Well, no. If you do a bunch of other stuff that's not this method, then it's actually different." Okay, well that's cool. Can we guys see this? There we go. So
yeah, there you go. All right. So when we turn the correction value off, like remember the blue line or the 0 is like the ideal prediction. And then deviations from that are these graphs here. So
can I
it's
ask
not,
something real quick? 0 being the arcs Hanover rise overrun, right?
yes.
Okay. Just want to clarify.
well, also
now
the actual elevation, right?
1 second. Now, for the globe to get the ideal measurement, right? A simulator was introduced where you give your distance and you have the refraction correction built in, but you subtract that out. But the way that you're subtracting it out, it's for comparison to the expected globe drop. So if the expected globe drop is the same as the what the refraction correction would be, you get a close globe match. So when you went out and did that, you verified Mike's methodology that the occlusion timing is based on the physical occlusion, and you also showed that the to get the globe result, you have to force it at an idealized location. You should be able to do that everywhere, but you can't. Look at what the graph is showing right now for all the measurements at different locations, randomized. You're not using a simulator to quote unquote predict where to go to find the idealized globe measurement.
Well, one of Goose's measurements actually matched the globe, and he had no idea ahead of time that that's what was going to happen, and he didn't go there for that specific purpose. But this idea that somehow because I was able to predict the results, that doesn't invalidate my location. I was 25 miles away. We all agreed that was a sufficient
I
distance.
didn't say that it invalidated it.
Okay, good.
You had to input that information first, though.
I could have
to get it.
So I could have got there just by trying a lot of things, but so
and hold on 1 second. In addition to Goose's measurement, that is, like I said, there's one spot per peak where there's going to be an idealized spot, and the elevation difference makes a huge impact on that. So him being at sea level, which is the same for what your measurement was, that you can hit that sweet spot. So that's fine. Like we have a bunch of random, like that. Obviously, if we get more data, it would be more clear or whatever. But so far, we've got like 40, 50, close to 50 peaks where it way more closely matches flat Earth than it does the globe Earth with a couple of measurements, and then one being specifically cooked in.
It's so disingenuous to say that any or others are from whose data set wouldn't match this thing.
Yeah, just so the reframing that you do to make it seem like from Mike's house where he started this doing different peaks that he like cooked it to make it seem like it like all these other ones are flat Earth. That's preposterous, dude.
Well, one of them was slightly closer to globe Earth, and one of them was closer to concave. But could I clarify something
When you say concave, you don't mean the inverse of the globe. You mean an entirely different thing with an entirely different radius value. Just to be clear.
Yeah, in that case, although there's situations that
In
might
all
match.
cases.
What? No. There may be situations that would match an exact concave of the official globe, but no, the 2,000 extra feet is not a.
Yeah, mathematically, you're probably right because that's the same thing that would happen to create the globe as well.
And I did actually find one in the simulator. But no, the 2,000 feet is not a 39, 59 mile radius concave, but it's still concave. It's still not flat. But could I comment on something about when I said that most of the data points didn't match flat Earth within a reasonable margin of uncertainty? So if you take all those samples at a given location, say Greenhorn Mountain, or all the samples for a single observer location and that same target location, you will see a certain amount of random noise, before applying these time shifting offsets, just the raw values. If you take the standard deviation of that, or even the peak to peak deviation of that, that gives you an idea of what a reasonable margin of uncertainty is. So when I say most of the data points are outside that reasonable margin of uncertainty, it's about like plus or minus 2 arc minutes, for example. Pikes Peak was just inside that. Rosa was definitely inside that. There's a couple that were, maybe 3 or so, that were inside that reasonable margin of uncertainty. Most of them were outside of it. That's what I'm talking about.
Well, you have your analysis. We have the raw recording timings and the deviations from that. So that's great.
And none of these match
Do
concave or globe, so I don't know what you're talking about.
do you have any other questions, comments, or
Yes,
concerns for this week? Because if not, we're gonna try
I
and
do.
wrap up a little early tonight. All right, go ahead. What do you
Yes.
got?
Yes. So, as a preface, are you still there, Dr. Mike?
I'm still here.
Oh, wonderful. Thank you. So, as a preface, I have been carefully checking some of the azimuth angles on the stars to which you applied greater than 1 minute of timing correction to see if that was warranted. And so far, I have not found any of them that I've checked that in any way warranted more than a minute of timing correction, not even close. So my question is, are you able or unable? And I did email these to you last night. I don't know if you got them, but are you able or unable to give an unambiguous example? By that I mean where we agree what time it was and which star it was and where it occluded. Are you able to give an example where Stellarium's time or azimuth is wrong by at least 60 clock seconds?
So, first of all, that sounds like a loaded question. But second of all, let me screen share this spreadsheet. Um, uh, this is all the stars recorded so far. In column A, it lists the peak. The rest of the columns, they give you the altitude of the peak, the distance between the peak and observer, the Latin lon of the peak, the final bearing of the peak, the Latin lon of the observer, or the altitude of the observer, Latin lon of the observer, the initial bearing from the observer's location, the date of the video, where the first frame of the video was when that was provided by the observer, which frame it was when that was provided by the observer, the time lapse, whether it was 1 or 2 seconds or something else. In column O, it calculates what the actual clock time is. In column P, it it lists the UTC time zone. It identifies the exact star in column Q. Just for those of us using actual cameras as opposed to night vision goggles, it gives the magnitude of stars so we can use that to help us determine that we're on the star we think we're on. It gives the right ascension, the declination of the star. There's a few comments in there. So it gives you credit for the ones where you identified the stars. We've got your hypothetical in there. And this is your revised hypothetical where you brought it a little closer. You'll notice that you still have a phenomenally high J value. So all of this data is here. Oh, and we calculate the d squared over r over 2r for those who are interested in that, and um, the hour angle theta t in column z. And then on these various tabs, this is the actual analysis running it through uh, uh, an algorithm that's indistinguishable from stellarium. So it gives typically the same answer to within a few arc seconds. And it does that from the peak location, from your observer location with atmospheric correction off, from the observer location with atmospheric correction on, and then it graphs it, and you can easily turn the timing correction on or off from the graph. So this is raw data, not corrected in any way. And you can see the red line in all cases is closer to zero deviation, the red line being the flat Earth prediction, than is the cyan globe Earth prediction or the green globe Earth prediction. The green being globe Earth prediction with no atmospheric correction, which is consistently not exclusively. There's a difference for Mount Rosa Jesse, the new one I added. That one is above the zero line, but the rest are below. The cyan line is consistently above the zero deviation line. So you can turn all this on and off. You can turn atmospheric refraction correction on and off. So you have total control over all these variables. And the bottom line is everything is much closer for flat Earth. Here's the big point of contention. This with timing offset on, the timing offset, what that does is it makes the green line globe Earth prediction perfect. It makes it exactly agree with what a globe Earther would predict by changing stellarium's timing until the actual measurement exactly measures what the globe Earth prediction is for that occlusion. And then it uses that same timing for flat Earth and for globe Earth prediction with refraction on. And this was the big surprise that when we cleaned up that with timing correction, you can see what a difference that made. No correction. There's some random variables in the measurements. We make that correction to the green line and everything cleans up. That's when I realized the whole explanation for this big dip and then you'll see on this one I added Greenhorn Mountain and North Peak. So they're both there, and you can see how the refraction varies between those. But the point is that's what tipped me off that the whole problem Stellarium was making is it was getting the final bearing wrong. So it was looking in the wrong location for the star, and that was easily corrected with timing, which is why the J factor corrects the timing. But the point is here, we're making the globe Earth prediction perfect, and what do you know? That cleans up everything, and that's what made it possible to calculate what the real angles were that were shown on slides 8, 9, and 10 of the introductory presentation.
So I don't think that answered my question, but it raised another. Can you turn off refraction and off the time and keep the timing offset to off. Please. Okay, so something's wrong here because with no refraction and no timing offset, the Blinn mountain points should have nearly zero error. So you are not correctly predicting what the globe would predict. So that's, you might look into that.
So your contention is wrong.
No, if you take the occlusion timings for my Blinn mountain from Edith's Hook, you put stellarium on the mountain peak at that time, read the altitude angle, that will be very close to the predicted geometric globe angle to that mountain. And your graph is not showing that lining up like that. So anyway, that's, you can work on that later. But I'm asking.
It's 22 arc minutes off of the globe prediction. Exactly. And the celestial refraction correction is 25 for Blinn.
So
I've forgotten whether Blinn was with refraction on or refraction off. Here's Blinn with no atmospheric correction, so it was consistently about 300 meters low. Here's Blinn with atmospheric correction, and it was also about consistently about 300 meters low. I remember your original diagram, and Blinn for flat Earth was consistently a couple hundred meters low. There is some kind of strange inconsistency there. We'll have to look into that.
Yeah, you can look into that. But I still, you've claimed that stellarium, when set to the observer location, occlusion time, and star, sometimes gives azimuth corrections or errors that is so wrong you have to correct it more than a minute. I'm asking for a single example of one of those where I can verify where a particular star occluded, that I will find that same error. Because
so
so
you
far
can
I've
look
not.
here. You can look here in column X, and that tells you how far Larium is off from the final bearing of the alleged peak. Now, you still have to go to your screen with a ruler or something to see how far off does it look like it actually is. But this is calculating it just based on the known final bearing from the NOAA tool or the movable types tool, as the case may be, and the value that stellarium corrects. So you can see these red values with no J factor. When we turn the J factor on, then you can see how that cleans them up. You'll notice a noticeable exception for Greenhorn Mountain, and that's because we know those stars were actually occluded far to the right of Greenhorn Mountain. In fact, it's almost on the video. If you estimate it, you might come to the conclusion it's about halfway. With the J factor turned on, it actually shows it's centered on North Peak. So some are to the right, some are to the left. So we can argue about this, but it does kind of miss the point that there's a radical difference between the globe Earth estimates from the observer location and the flat Earth estimates from the mountain peak that's entirely corrected by the J factor. And even without the J factor, you can see the red line is much closer to zero than are the green line or the cyan line. So in all cases, whether correction is on or off, the flat Earth is the most correct prediction, and the globe Earth predictions are way off, either with or without correction. It doesn't matter whether you have the correction on or off. The only thing correction does is smooth it out, and makes it a lot easier for us to see what the actual relationship is.
He went out and did it. and try to find
So
the globe.
you showed IPUP there, right?
IPUP should be the first one at
To find the
Greenhorn
globe.
Mountain or North Peak.
Well, you've got IPUP listed twice, once for Greenhorn and once for North Peak.
Right, because of the discrepancy of which one is it closer to. There's a disagreement about that. With correction off, it says that let me see. It says it implies that it's closer to Greenhorn Peak. There's more green values for Greenhorn Peak than there is for North Peak. With correction on, it says those stars are almost perfectly centered over North Peak. So there's a debate, and I think everybody agrees it's not over Greenhorn Mountain. It's way to the right of Greenhorn Mountain. The big point of contention is how close to North Peak is it?
Right, I
And
don't agree on that
so you
particular
don't
one.
agree, and that's fine. And that's why we went over the basics, because you're arguing about things that don't matter once you understand that every single globe Earth prediction starts from a flat Earth prediction, and it either adds or subtracts to that to get the globe Earth prediction. That's that's what those. In fact, I'm gonna stop sharing this and go back to sharing that. The uh, so I'm going to go back to the equations. Um, this is what these equations are showing. This is where globe Earth angles come from. They are the uh, globe Earth theta sub g starts from flat Earth, and it subtracts the distance angle, which is the distance angle being 360 degrees times the distance over 2 pi r. And in the case of the globe Earth refraction estimate, that starts with the globe Earth angle, which is actually the flat Earth angle minus the distance angle, and then it adds GG Bennett refraction angle.
Sir?
So all of your globe Earth angles are actually flat Earth angles with little offsets added or subtracted to disguise them as globe Earth when they're actually all based on flat Earth.
All your angles now
Sir?
are belong to us.
Could I share my screen and could you look at it, Doctor?
Why are you doing that,
Go
Doctor?
ahead.
Would you also with this rise over the run principle, if we know the run to the GP of the star, we could work out the height of the star, surely.
All right, can you see my screen?
I see it.
Okay, so I did a very careful analysis of this. So this red line is where I traced the actual mountain horizon line from your video before it was too dark to see it. And then, as you recall, you commanded the telescope up a little bit to get rid of that flashing strobe light. And then I determined where the new horizon position was based on where every star disappeared. So as they disappeared, they all disappeared at this line because that's where the new horizon was. This here on the left is Greenhorn Mountain. And this here on the right is where IPUP set, right in this little V here. And you can see I've lined up this star with, I overlaid this to Stellarium. I lined up this star, PR pup, and IPUP, all with Stellarium. So I know that I've got it synced up good, okay? So what happened when you're claimed, of course, you know that, or we all know that your C star only has 44 arc minutes of field of view width, right? So we know that this is Greenhorn Mountain in view, and we know that the distance between Greenhorn Mountain and North Peak is about a degree. So when you corrected IPUP that much to put it over here, you actually are claiming that it set at an azimuth that is not even on the screen of your sea star at that time. So, and when I calculated, I took the mountain peak here, just like you said, the mountain peak of Greenhorn. I counted my pixels, and I counted, and because I've got 3 stars here in a pattern, I can look up the azimuth angle of those, and I subtracted the azimuth angle from HD 5681813 from IPUP to get the number of degrees of span, and then I use the measure tool to measure the pixels in my image editor. So I know how many degrees per pixel. So I know for a fact that the azimuth of this star, where it actually physically set, was approximately 200 degrees, 45 minutes, and 12 seconds. And look how close, that's within like, what, 15 arc seconds of what Stellarium said. That's within less than a minute's of time. So there is no warrant for us to say that we need to correct IPUP by more than a second or two of time. It was not
So,
drastically out.
yep, I did a very careful analysis of your analysis. You failed to disclose this is from the observer location, and so you're not dealing with final bearings, you're dealing with initial bearings. And uh, all of our adjustments are based on final bearings, not on initial bearings. So you're comparing apples and oranges and making it look like there's a huge difference when there's not a huge difference, and you're missing the more important point, um, that um, there is a discrepancy in the bearings. That discrepancy can easily be resolved by just shifting the stellarium timing using the J factor. And the J factor from the very beginning, it was just touted as an easy way to correct for the stellarium um, miscalculation. And we know the miscalculation is there because stellarium got the final bearing wrong. And when you look at the spreadsheet column X, I think it was, you can tell exactly how much it got that final bearing wrong by. Yeah, that's in
What do you mean?
column X.
What do you mean about
So
the final bearing wrong? Got the bearing from on the mountain, the bearing to the star
Right.
wrong at that time.
right. Because we know what the final bearing of the star we saw occluded was, and that's not what stellarium is reporting from the peak. That's what
Well, it won't do.
what tipped me off that stellarium was doing a calculation error. And I'll take you back to look how the J factor cleans up the globe Earth prediction.
Yes,
You've said many times is fixing the flat Earth prediction. Well, it fixes that by default because your globe Earth prediction is actually just an offset from the flat Earth prediction, and it helped us uncover that fact that all the globe Earth prediction is a flat Earth prediction minus distance angle, and in the case of the globe Earth refraction on correction, that is the flat Earth minus the distance angle plus the GG Bennett angle. So you're literally all you are doing is adding or subtracting from flat Earth predictions to come up with your globe Earth predictions, and you think that proves a globe Earth, and you don't seem to realize as your correction factors go from towards zero, so you go to no correction, like when you get right on top of Flynn Mountain. Then all of a sudden, there's hardly any difference, and for a while, you were trying to find as little difference as possible for that very reason. It made them basically the same prediction. But
The point is
that's the
that
point.
bearing to the star is going to be different
And
for a
real
true
quick,
issue, isn't it?
lads, 10 minutes. We're gonna wrap up here. So if you guys want to close on this conversation, or if anyone else, real quick before we wrap up, has any questions, If not, we'll close on this point.
I have a question.
Go ahead, sir.
So let's see. So Shane did send, because I haven't really been briefed on a lot of this. Shane sent the PDF, and I see in here an equation that relates peak altitude, observer altitude, distance to peak, and the occluded star elevation. And I'm wondering mostly about the occluded star elevation. If anybody could tell me what the units on that are, because you're using tangent on what looks like a distance instead of an angle. It's very confusing. What's going on there?
Can you share what Shane sent you?
Yeah. I'm just gonna take a screenshot and put it in here.
Page roughly would be on.
Here it is. This is on page 2, right at the bottom of page 2. Methods compared. Because I'm not really sure how you guys are predicting these. I don't know what you guys are using to actually predict any of this, and
It's just the
yeah.
tangent of the rise over, or it's just the tangent times the distance of the angle. The tangent of the angle times the distance, plus the observer distance, or height.
Okay, dimensionally that doesn't make any sense.
It does. If you're at an X
If
elevation,
if the units of that are specifically distance, that physically doesn't make sense, because angles don't have units of distance. Is occluded star elevation?
that's an angle. Elevation in astronomy, the angle to a star is called the altitude angle or the elevation angle.
Okay, perfect. And so there isn't a lot of technical explanation in here. What is this? This is just the formula for the peak altitude. What is going on here? Are
The
we predicting the
elevation
altitude of the
prediction
peak?
at the time of occlusion.
This is from the section where you can backwards derive what the altitude of the peak would be based off of the observer altitude and the distance to the peak and the time that it was, or the angle that it was occluded. So it's just like a
They're
backwards
just
derivation
so what they're
to get
doing.
what
You
the
guys
peak
are
would be based off of the angle.
right. This is like basically as if you were looking at what the angle of the top of a tree would be on a flat field, right, from a certain distance away. If you know the height of the tree, which would be the altitude of the peak that's doing the occlusion, right? And then the person that's standing on the field would be the observer location altitude, and then you guys are calculating the tangent function to calculate the angle that the top of the peak would be, right? That's essentially what's.
And so the big. Let's see if I get this right.
Roxanne, rise or run?
Yeah, I'm past that. That makes sense.
The problem is that we already know that when people do this over a flat Earth from sea level, over known, when they take a theodolite and they look at the angle of a peak of a known distance away, we already know that triangle doesn't actually work. It doesn't correctly calculate what the angle of elevation would be for the peak.
Fairly obvious. So I also see that you guys mentioned that the flat Earth, I think right at the bottom, observations from Alan. You guys don't need to use the observer's position to define angles. Where I'm very lost on that, because if you're using distance at all to anything, then that just implies location.
Well, I have a kilometer, 57 50.7 kilometer long theodolite. That's how the conceptual theodolite works,
No,
right?
no. What he was asking. So we could backwards derive the distance based off of the mountain peak elevation and the time that it was occluded. That's what I meant about the distance, if that's what you're referring to.
Yeah, yeah. That seems a little. I mean, if you have angles, then you have points, and points require position. So, was there anything? Was that just the entire idea with that?
Yeah, so if you use the
Okay.
globe geometric position for a true position, you would get the wrong distance because it makes a different prediction. It says that that star is way lower at that distance.
Mhm.
Is Doctor gone now? He is, isn't he?
Yeah, we got about 3 minutes, lads. So
Just, I mean, this Arctan Rise of a Run and the trigonometry is good. I mean, would we all agree then that if we know the GP of the star, we know the run? Could we work out the rise? Could we work out the altitude of stars this way?
So here's the thing. The way that they did it for celestial navigation specifically, using the fictitious observer that we talked about, and that's known as geocentric coordinates, what they do is by setting that observer to there, they set the celestial sphere altitude to the same as the quote unquote terrestrial sphere. So that the way they talk about it is they say, imagine you're at the center of a hollow sphere, the Earth, and you're looking up, and instead of seeing the stuff at the surface, you're seeing the planets and stars and everything attached, forming a dome around you.
It's not an answer to my question though. If you know where the GP of the star is, you know the run. If Arctan Rise of the Run works, surely you get a rise, don't you, to the star?
So listen, you're talking about getting the actual altitude of the star, right?
Trigonometry.
Well,
right,
I just
here. Right. So listen, and I'm telling you to use celestial navigation. They set it to an
avoiding what
altitude
I'm
of
asking
39.
you.
Stop to an altitude of 3959, so that there's a 60 mile per degree relationship or 69 mile per degree relationship between the elevation angles of 30 and 75 degrees when you're
This
when
is
you're
not
looking.
what I'm asking you. If you know the location on the Earth at a moment in time when the star is at zenith, you've got your run. Do you know how far across the surface it is from you to that person? This rise of a run, you can plug this maths in, you can get a rise to the star. This arctan, if it's got any value.
I'm telling
I'm
you
talking about the center of the Earth. I'm talking about a flat Earth now.
I know. I'm telling you what the elevation is because the elevation is just an apparent object, right? So like you could calculate all kinds of different things, making different assumptions. What I'm trying to explain to you,
including
what I'm
the
trying
problem.
to explain to
I
you.
think Paza. I
Stop,
can explain it a little
please,
clearer for Paza.
sir. What I'm telling you is, right, using different assumptions, you can get different elevations. So the way that they made the globe work is within that threshold. That's what I'm trying to tell you is by setting it to that specific elevation, what that comes out to when you multiply out the latitude lines, you get 60 times 90, you get 6210. So like that gets you the quote unquote curve distance on Earth using the same.
This is not an answer to what I asked you. And
It's
if Arctan
what the
Rise of
elevation
a
would
Run,
be to get the star. You could get different
Alan,
things. That's what they're
if
using.
Arctan Rise of a Run is good for the mountain, why is it not good for the star? If I'm directly under the star, I've got my run.
Because the mountain has a physical location, bro. I mean, come on.
I'm trying
So
to
does the
tell
star,
you.
doesn't it? If the star,
And you're
No,
assuming the
well, then
star
why are
doesn't
you
have a
using it as a
physical
reference?
I'm trying
location.
to tell
Then.
you that the thing in the sky is apparent, but so the elevation that they have set for it for usefulness, because you can get different calculations based off of different things, is 3959 for the actual elevation.
If it's apparent, you can't use trig on it then, can you? Because if you can't use trig on it when it suits you, you can't use it ever.
It's not what I said.
That's what he said.
Said if you're
Okay.
going to relate it to a position on Earth for the in relation to latitude and longitude, then you're going to set it to an elevation of 3959. I'm explaining to you what that rise would be. Because making different assumptions, you can get different rises.
I mean,
There's no
I think
no physical. Here's a better way to answer your question. the calculation that you would get for the actual altitude has no physical meaning.
But what
There,
Paz is getting at though is we know that
Okay.
on the globe, there's an explanation for why if you're at or near the North Pole, Polaris is going to be directly at your zenith. If you're at the equator, then the sun at its highest point on the equinox is going to be at your zenith. And then we know that if you're 69 miles or 60 nautical miles, north or south from those locations, you can you can you can already know, because we're traveling the curve of a sphere. It explains why the angle would be what it is at any given location between there. That's like the basis of celestial navigation. You guys are using the tangent function on a flat Earth, in which case you should be able to use a tangent function to determine, once you set some arbitrary value for any of these objects, you should have a tangent function that you could then use a flat Earth geometry to calculate the angle to the distance to any angle on any celestial object for all locations on the Earth. But obviously that doesn't work. That's something Globers have been asking for a long time. It seems like that's the crux of this issue. We
No,
have to
Nope.
figure out why
Okay,
why
hold on
doesn't
one
tangent
second.
why doesn't a
What you
tangent
didn't,
function work on a
and
flat Earth? That's the
I can
question.
address everything you just said, because I've already addressed it multiple times through here. So if you look at the main chat real quick, our contention is that the 69 degree relationship is optical, and in addition to that, that relationship only holds within the elevation angles of 30 to 75 degrees. Within outside of that, you have to apply aggressive correction factors to explain why the stars don't maintain a 15 degree per hour relationship. Now, secondly, when we're talking about the elevation and the setting of that, if you look at what Shane posted at, what time is that? 8, no, was that 10:01? If you look at what Shane posted at 10:01 there, you'll see the concept of the celestial navigation that you're referencing, right? So the fictitious observer that's tying all these zenith measurements with respect to the first point of Aries to give us where they're at in time, to relate it to a ground position on the ground, you have to set it to a radius of 3959. So to use the celestial sphere and the terrestrial sphere, you have to overlay them where they intersect with the z-axis of an observer at the center there. That's what we're looking at. Now, if you multiply that out linearly with latitude lines based off of 69 miles per degree with Polaris going from Polaris to the equator, you get 6210. That's going to be the statute miles. If you use, nautical miles. If you use statute miles, you get like 6218 or something like that, right? So this whole scenario right here, based off of positions and angles of the stars with respect to time, is using a fictitious observer at the center of it to compare to. And when you talk altitudes and all of that, and is the trig valid? Like I said, making different assumptions. Like if you assume, for instance, that you're standing on a sphere of a radius of 3959, and there's a celestial sphere with infinite radius, but you arbitrarily set that radius to 3959 so that you, and I say arbitrarily, but it matches the terrestrial sphere coordinates, so that they have an intersection point. That's what they're using to do that relationship. So what you're looking at is an observer with an azimuthal grid of vision, and the way that you see the stars is latitude dependent and within that. So this relationship that you're seeing is an optical one. So that's the point
Shane,
of the celestial theodolite, to test that. Yes, go ahead real quick, and then we're going to wrap up. You can get the last word. Go ahead.
Shane's animation is lovely, but he's got stars going under the ground.
Well,
no,
it's just a
no,
mapping of
no, it
negative
doesn't.
coordinates. That has
It
nothing to do
specifically
with the
doesn't.
shape of the
Oh,
ground.
No, no.
whatever that means. Where do the stars go then when they go over the horizon?
the
So real quick, we'll cover that. That's a great point of contention, right? Is the mathematical function of negative coordinates indicative of stars being beneath your feet or being above you, circling you, but being out of your field of vision, which is a dome of vision? And when things are out of your dome of vision, they arc to the horizon because that's where the sky meets the ground. Would the math function be different? No. No.
How do you know that?
The negative
Talking about
coordinates don't tell us anything other than it's out of our field of vision.
if I put a gun to your head, Alan, you couldn't draw it.
It's
But
there's literally a diagram of it.
the
Yeah, that's
problem
not
with
a
Shane's
diagram.
animation too, Pazda, that you missed is that, okay, that's all fine for one observer on that flat plane, but if you start adding an observer at every location on that flat plane, there would be no consistent way to be able to determine.
It's
Ooh,
the
Yeah,
personal. It's
ooh,
the personal
great,
view. The
great point of
personal view.
contention. No, that's a great point of contention. So the to use this coordinate system, right? You have to know your time so that you can know where the star is going to be with the angle to it. So Shane, if you're still there, if you want to give a quick recap of how celestial navigation was done before the introduction and mandatory use of this coordinate system, it was done via run lines.
Oh yeah, right.
So nobody was navigating in this way that is said to be mutually exclusive to a globe. Now, what it is mutually exclusive to is time and the coordinate system in which it's using, which is spherical. I agree completely. But here's how they used to navigate independent of stars going beneath your feet and all that. Go ahead, Shane, and then we're wrapping
It
up.
seems like a roundabout way to try to get around the fact that it was just brought up that multiple observers make it to where you have to have aggressively bending light in multiples of tens of degrees for different observers versus this quote unquote aggressive correction that the globe would need below 15 degrees, which is only to adjust it by about a half a degree.
Well, nobody sees anything beneath their feet though, so I don't know like what aggressive correction you're talking about though.
I don't know what aggressive correction you're talking about to say that it aggressively needs to be corrected to adjust for half a degree at the maximum.
Celestial refraction coefficients are outputted calculations that aren't derived from any physical process. They're purely computational based off of a computational model, assuming smooth gradients and assuming the globe as the input for the radius and then distributing that smooth gradient atmosphere.
Those
out.
aren't bad assumptions to make.
Here's the problem, though. If we
Hold
take
on. No, how are you going to interrupt me in the middle of me explaining something? Like,
Because
you're
it was
sorry,
not because it wasn't an actual
I'm not talking to
explanation.
you. There was another person, dog. So just relax. There was
I
another
am that
person.
person.
There was a different person who's not you who was trying
Yeah,
to interject.
Jake on the plane was also getting in. Two people were interrupting Alan. Dr. Brian
So-
Peck and Jake on the plane.
So real quick, when I say aggressive, right, they're just computational outputs derived to fit what the globe has to have it to maintain usefulness of that coordinate system because the angles correspond to time. So when I say aggressive, that's what I mean. It's just a computational output that's a curve fit. It's not derived from any physical process. When you say that's not bad, when you say those aren't bad assumptions to make, yeah, if you're trying to force a coordinate system, yeah, then that's not a bad assumption to make. You're absolutely correct. But it doesn't have any physical relationship to reality. So how you get it to work might not have any relationship to reality. That's why we're testing this conceptual model here with the celestial theodolite.
You're actually
But
testing that. And go ahead, Jake.
Yeah, I was going to say, but in the end, if you look at, for example, the sun on the equinox when it's on a given meridian, when it's directly overhead on a meridian, for every observer on that meridian from the North Pole to the South Pole, you can calculate for any given location 1 degree every 69 miles or 60 nautical miles to predict what that angle of elevation for the sun would be, right? And there's no flat Earth explanation for why that would be the case.
Yeah, we just explained it. It's optical based.
But what's the physics behind that optical base that would create this relationship? Where's the math behind that? Where's the scientific experiment that shows what's going on to create this optical effect? When you're on a flat Earth, why isn't it following the tangent function? Why is it doing this weird 69 miles per degree thing?
Oh, there's lots of experiments that go over the visual space and how we see in a dome. And
Jesus Christ, answer your question without answering it again. Why don't you?
What do you mean by we see in a dome?
Oh
What do
my
you mean by that?
god.
This has anything to do with the celestial theodolite, but all of your duck diving and dodging is
No,
noted.
this is true. This is true.
I mean, there are plenty of things like the celestial
When you
sphere
open up-
is not.
On the stupid idea
Oh,
that
boy.
there's a
when you open up
it's a
celestial
dome
navigation
vision.
manuals,
It's an entire idea of a
when you open up celestial navigation manuals, right? When you read books from astronomy of old, the first thing that they say is that we appear to see the domes we appear to see the heavens as if they're in a dome. But don't be fooled, it's actually the ground that's curved. So that's like premise number one for the backbone of it. And then on top of that, there's experiments called the alley experiments. There's also several different variations that have been done where if the visual space and the spatial field are the same, then there will be no deviation. But what they show in each experiment is at different distances, at different having the observers complete different tasks, is that there's actually different types of optical curvature that we see in. Now, a big function is, or another easy way to explain that would be train tracks on. They appear to converge at a distance, and then when you look at a building, when you're standing next to the building, when you're standing close to it, you can't see the details of the edges of the building, like up at the top. But as you get further away, you can start to resolve more. It's the same exact relationship. Your eyes create the information loss. So when you're saying like there's been no flat Earth explanation, you've literally heard it multiple times and then reasserted that you've never heard it before. So we're gonna actually end on that one for realsies this time, and then I'll be back to do like another maybe 10 minutes of this. But I'm gonna wrap up the stream now so that everyone who was so Mike and everyone can go. So I'll be back.
All right.
Excellent. All right. So that was great. Thanks everyone for tuning in. We're gonna do some more squabbling and then probably hang out with Witsit and analyze his debate. Maybe we'll see. See what goes on. Thanks everyone.
Welcome to the show where you don't know if it's part of the show. Welcome to the show. If you don't know, it's part of the show. Didn't they teach you to reach for the stars while opening up the bars and keeping you chained down with mortgage bills and cars? Vaccines for your arms, kids sounding like supercharged, caffeinated hate-filled scars and rage-quit repertoires. No answers for yards, caught up in emotion that's not even yours. Imposter truths like impeccable retards, lined up for your serving of Gish Galloping wars. No remedy can't save the lost, in love with the yarn. I'm tired of walking into refracted shards, poor science displayed by disgusting bards. Soaked in sin with your dupe is delight and a new hand of cards. Been so long, seems like for love I'm just too hard, I'm just too hard, that's it. Welcome to the show where you don't know if it's part of the show. Welcome to the show. If you don't know, you don't know. Intoxicated 8 makes you believe you're spinning in space while you have no shame or grace. It's a disdainful state I used to contemplate, how to save myself from my own self-hate. Wonder why I was even made with a dreadful fate, forced to try and awake with a full plate. No one to help me stay awake or educate. I've had to liberate and fight through hidden gates. But my brother, heaven could never be late, and rockets don't work in space. It's all fake, the show is on Mars. It's a joke, but you're too far gone, it won't be long. Fepe's beak is strong. We have our song and we march along like streams of knowledge leading to God's holy pond, and lives of truth that hits the bong and sings the song, turns mankind from the wrong. We come in peace with a holy gown and all of us wearing our holy crowns. Said the earth is flat and we probably just won't get along, just to go along. I said, welcome to the show where you don't know if it's part of the show.